Understanding the acoustic modes of a room is essential for predicting sound behavior, controlling resonance, and improving acoustic performance during the design stage. Hello, I'm Armin. Today we have a fantastic ANSYS tutorial on calculating the natural frequencies and corresponding acoustic modes of two rectangular rooms. This video was created in collaboration with Laplace Academy. Before we begin the simulation, I'd like to briefly explain the model and the physics behind the analysis. Let's get started. Rooms are present in almost all homes. A room is a three-dimensional acoustic system with many natural frequencies. When the room is small or when the sound frequency is low, the modal density becomes low. In this condition, sound behavior undergoes strong fluctuation in modes. At higher frequencies, the modal density increases significantly. In this region, the sound field becomes more diffuse and the behavior is less dependent on individual modes. In a room, acoustic modes are classified into three categories based on how the sound pressure varies. First, axial modes. These are one-dimensional modes where the sound pressure varies along only one direction between two opposite parallel surfaces, such as the front and back walls or side walls. Second, tangential modes. These are two-dimensional modes where the sound pressure varies along two directions at the same time, involving four room surfaces. Finally, oblique modes. These are three-dimensional modes where the sound pressure varies in all three directions, and reflections occur from all six room surfaces. ANSYS uses the finite element method to calculate natural frequencies and their corresponding modes, and is capable of solving complex geometries. We use a modal acoustic system that employs an eigenfrequency solver, which is a common method for finding natural frequencies and mode shapes. Finally, we will view animations of the resulting mode shapes. In this video, we will use two rectangular rooms because it's easy to validate the results using analytical formula. The first room has a length of 4 meters, a width of 5 meters, and a height of 3 meters. The second room has the same width and height, but a length of 6 meters. All walls are assumed to be perfectly rigid, with no acoustic absorption. In a room with rigid walls, the natural frequency depends only on the speed of sound and the room dimensions. After solving the model in ANSYS and comparing the results with the analytical solution, we can see excellent agreement between the numerical and analytical results. Finally, I'd like to introduce the reference of this video, Sound Insulation in Buildings, written by Jens Holger Rindel. Chapter 4 of this book covers room acoustics, where you can find the analytical formula for a rectangular room. Now let's begin the modeling process with a beautiful AI narration.
The calculation of natural frequency is an eigenvalue problem. Therefore, we need to use Modal Acoustics. I will double-click on Modal Acoustics in the left toolbox. Before starting the analysis, I want to adjust the speed of sound to match the value used in my MATLAB script. For this reason, I will double-click on the Engineering Data cell. By default, air, structural steel, and water liquid are already available in Engineering Data. I will click on air, change the speed of sound to 343 meters per second, and press Enter. I will leave the other properties unchanged and close Engineering Data. Now the next step is creating the geometry. I will right-click on Geometry and select SpaceClaim. You can also use Discovery or Design Modeler if you prefer. We are now in SpaceClaim. Before starting, I want to change the work plane. I will click on Select New Sketch Plane, choose the XY coordinate plane, and then click on Plan View to switch to the normal view. I will start by drawing the room's base. From the sketch ribbon, I select rectangle, then click at the origin. I type 4,000 millimeters in the X direction, press Tab, then type 5,000 millimeters in the Y direction and press Enter. This rectangle represents the room's base cross-section. Now I click on End Sketch Editing. By pressing the H key, we can switch to the perspective view. Next, I need to extrude this rectangle 3 meters in the Z direction. The pull operator is selected by default. I simply click on the surface, type 3,000 millimeters, and press Enter. The geometry is now complete. I press Escape. There's nothing else to modify, so we can close SpaceClaim. The third step is preparing the model. I will double-click on the Model cell to open ANSYS Mechanical. Now we are in the ANSYS Mechanical module. In the Outline section, I will expand the Geometry node and click on the solid part. In the Material section, I need to assign air instead of structural steel, because in acoustic modal analysis, the room volume is filled with air. Everything looks correct. I will collapse the Geometry node and click on the Mesh node. The element size is currently set to default. I will right-click on Mesh and select Generate Mesh to create the default mesh. The default mesh is suitable for this model. There is a rule of thumb for defining the maximum element size in acoustic analysis. The element size should be approximately 1/6 of the wavelength to properly capture the acoustic modes. Now we need to adjust the analysis settings. I will click on Analysis Settings. For acoustic modal analysis, we need to enable damping under solver controls. If we do not enable it, the solution will not converge. All room boundaries are rigid by default, so there is no need to define additional boundary conditions. In the maximum modes to find, I will change the value from 6 to 10 and press Enter. I will leave the minimum and maximum frequency range as default. At this step, we only need to solve the model, so I will right-click on Modal Acoustic and select Solve. The solution is now complete. If I click on the Solution branch in the outline, we can see the natural frequencies in the tabular data section. Now let's visualize the acoustic mode shapes. I will right-click on Solution, go to Insert, and select Acoustic Pressure. By default, the first mode is selected. Next, I right-click on Acoustic Pressure and choose Retrieve this result. Now the first mode shape is displayed. Let's click on Play Animation. From the animation, we can see that the wave propagates in the Y direction for the first mode shape. The corresponding natural frequency is 34.3 Hz. Now let's compare this result with MATLAB. The MATLAB solution also shows that the first mode shape is in the Y direction, and the natural frequency is exactly the same as the ANSYS result. This confirms that our numerical model in ANSYS is correctly set up and validated against the analytical MATLAB solution. We can also visualize the other mode shapes corresponding to the natural frequencies listed in the tabular data. I will right-click on Acoustic Pressure and select Create Results at All Sets. As you can see, 10 mode shapes have now been created in the Acoustic Pressure folder. However, they still need to be evaluated, so I will right-click on the Solution node and select Evaluate All Results. Now all mode shapes are computed. It is better to adjust the names for clarity. I will select all the acoustic pressure results by holding the Shift key. Then I right-click on one of them and select Rename based on definition. All names are correct except the first one. I will right-click the first result and select Rename based on definition again. All result names are now properly defined. Next, I want to add a parameter for the room length and calculate the first natural frequency for two different lengths. To do this, I will close ANSYS Mechanical and reopen SpaceClaim. The room length is in the x direction. To define it as a parameter, I go to the Design tab and select Pull, or simply press the PP. I click on one side of the room, then choose the ruler option. After that, I click on the opposite side to define the reference distance. We now see a P symbol, indicating that this dimension can be defined as a parameter. I click on the P symbol to add this length as a design parameter. Then I press Escape. Let's check the parameter in the Groups section. We can see parameter 1, which represents the room length of 4,000 millimeters. It is better to rename it. For example, I will change the name to Length. Everything looks correct. Now I will close SpaceClaim. Now the parameter set is added to the Modal Acoustics system. The model needs to be updated. I will double-click on the model cell and click Yes to update. ANSYS Mechanical starts updating automatically because we defined a parameter in SpaceClaim. The yellow lightning symbols indicate that the model needs to be solved again before we can use the first natural frequency as an output parameter. So I will right-click on Modal Acoustic and select Solve. Next, I want to define the first natural frequency as an output parameter. I click on Mode Shape 1. In the Details section, under Information, I check the box for damped frequency. Now, a blue P symbol appears on the left side of the damped frequency value, which is 34.3 Hz. This means the first natural frequency is successfully defined as an output parameter. Everything looks correct. I will now close ANSYS Mechanical. Back in the parameter set, we can define a new room length. In the table of design points, different length values can be specified. DP0 is the default design point with a length of 4,000 millimeters. I want to calculate the first natural frequency for a room with a 6-meter length, so I enter 6,000 millimeters in the length column and press Enter. In the parameter set, the D column shows the Retain option. This option determines which solutions will be saved in the ANSYS project file. If I deselect a design point, only the parameter results are kept, and the full solution data will be deleted. Since I want to keep all information for both room lengths, I will make sure both design points are checked. Now I right-click on DP1 and select Update Selected Design Point. The solution is completed. The first natural frequency of the room with a 6-meter length is 28.58 Hz. Next, I will solve the model again for the previous length. I right-click on DP0 and select Update Selected Design Point. The solution is complete. Now we can compare the results of both designs. At the moment, the model is set to DP0, which corresponds to the 4-meter room. If I want to see the updated geometry and mesh for the 6-meter room, I right-click on DP1 and select Set as Current. Now let's go back to the results. This is the room with a 6-meter length. The results show the natural frequencies and their corresponding mode shapes. As we can see, increasing the room length decreases the first natural frequency, which is physically consistent with acoustic theory. The tutorial ends here. Thank you for watching. If you found this helpful, please like the video and subscribe to my channel for more ANSYS and COMSOL tutorials.